Anybody mind if we audio record this as well? Since it's going to be on video.
Yeah. No, just video is enabled. No.
Just want video, we don't want the audio. Okay, no, record. Yeah, it is. Yeah. All right. So what I want to walk you through today is, actually I'm going to follow Dino's guidance. Dino called this thing Engelbart P1. And so what I want to be able to do is highlight my understanding of some, not all, of Doug's key contributions, and in particular focus on his non-technical contributions while not ignoring his technical contributions. Okay? And then the plus part of it is going to be, what does that mean to me, and what is the set of initiatives that I'm working on, and how is that derived from what Doug's work was. And then the last piece, I'll give you a few examples, and in particular then talk about how we might be able to collaborate. So that's what I kind of prepared, but clearly this is a topic that's central to me, so many other related topics can come up in conversation as well. And I invite you to do that often. Okay? That'll make this more interesting. Okay? Now, in so doing, I'm pointedly using something that's not PowerPoint. So let's see how this works, all right? All right, let me go to the next page. Okay. So I'll tell you a little bit about myself because I think this might be useful. Is this readable? Okay.
It's a little bit easy.
It's not super well focused.
It cannot be focused well.
It was.
You can try, but you cannot focus it.
It's good.
This is good? Okay. All right, so just a couple minutes on this. And the reason I want to spend a couple minutes on this is because we can look for where there are commonalities with my brother Dino. Okay, so I was born in Taiwan, way before you guys were born, maybe even before some of your parents were born, we'll see. And my dad was a mathematician. He was one of 7 brothers and 4 sisters. My grandfather had 11 children on my dad's side. My mom's side, there were 5 kids. So my mom was one of 2 daughters and 3 sons. So because of that, I have somewhere around, what was that, 15 uncles and aunts. And to my latest count, and this is just what people will admit, I have about 36 cousins. I think about 2 dozen on my dad's side and about a dozen on, I'm counting myself in that dozen on my mom's side. Okay, born in Taiwan, and actually not in Taipei. You know, most of the island of Taiwan is actually in Taipei. It's very rare you run into somebody that's out of Taipei. But I was born in Tainan, not really means south. Okay, so the south side of the island. And to give you a little bit of context, most of this last 40, 50 years, Taiwan has been around 20 to 25 million people. And that composition is of 3 types. There's a set of people, around 100,000, 200,000 people called Aborigines, who are native on the island with Polynesian background. There's about 18 to 20 million that really came over from China over the last 300, 400 years. Okay, so not this past century, not the 20th century, it was way before that. And in particular, my family derives their lineage on Taiwan way back to about 1720, approximately 1712 or 1720. And then there's the last wave, which is around the 1940s, late 1940s, which is when Mao was creating his system over in mainland China, and then the nationalist Chinese, the Republic of China, decided that they had to escape this heat in China. So they came over to Taiwan with the entire army, with many of the national artifacts, with much of the nation's cash assets. So anyway, that's a little bit of Taiwan history. I'll refer to some of that later on. My dad really came to get his PhD. He was kind of a rebel. And by rebel, I mean that it was very prestigious in Taiwan to be a doctor. But my dad was the only non-doctor of all his brothers. All of his brothers are dentists, internal medicine, eye doctors, whatever. But he was the only mathematician. He's the black sheep of the family. Okay. So he was able to get a PhD position, scholarship at Stanford. And so after about 3 years, when he was ready to get his degree, that's when my mom brought myself and my brother came to the United States. That was about 5 years ago. So, long story short, he said, if you take one piece of advice from me, only piece of advice he was going to give me was don't be a mathematician.
What? Don't be.
Don't be a mathematician.
Okay. You're listening.
So I tried everything. I tried aeronautics, I tried chemical engineering, I tried medicine, I didn't like it. I tried music, but eventually, after I tried everything, the easiest degree to complete was math, because I had run out of time to complete any other degree. Okay. Now, it turns out that I would have done software if there was a software degree at Stanford, but that was so long ago, there was no undergraduate software or computer science degree. Now, the very next year after I graduated was the first year they started granting a computer science degree. I actually don't like that, by the way. I like the math. I worked for a couple of years, and then I went and did a MS&II program. Okay, it didn't actually complete it. I want to be very clear about that. I don't want to misrepresent. But I did the coursework, and I did most of the practicum, which is the programming project and the science project. The reason I didn't complete was that the company I had worked for about 2 years, the company that sent me to Stanford for my master's program, had this research project. The research project was attempted by 2 or 3 principal investigators, and it didn't really go anywhere. The government said, no, you're not on the right track, you're not on the right track, you're not on the right track. So by the time they tried all those people, I was the next person in line. So they said, do you want to run this research project? And so I did, and that actually turned out to be quite a fun project, but the side effect of it was I never actually completed my master's degree in Stanford, nor a PhD. The research project was this. There was a project, in fact it was the sister project of the Stratus project, Jack. There was a project where the government wanted to build a cartographic information system. And it wanted to put together a lot of kinds of information. This is what the government used to call intelligence fusion. They wanted to take all sorts of intelligence or information and fuse it all together, and then use that to do all kinds of different inferencing or search. And they were willing to make all kinds of data available. They were willing to make mapping data, terrain data, weather data, equipment data, weaponry data, communications intelligence data, antenna data, propagation models. They were willing to make all of that available if we could just put it all together and figure out how to do it. Now, the reason I had done this was because the company I was looking at was specializing in image processing. And image processing was relatively new at the time. There was a satellite system called Landsat, which was not extremely highly classified. It was classified, but not extremely highly classified. And so the company was actually started by Bill Perry. Bill Perry ended up a couple of decades later becoming United States Secretary of Defense, I think under Clinton. But he started this company in the 60s in order to provide a service to the United States government to process and analyze imagery data from the Landsat. We had also been doing this for U-2 planes, which at the time nobody could talk about. So the fact was we actually had a lot of compute power in order to process data, and now with this variety of sources, we could actually attempt to theoretically build these systems, but we had tried multiple times before and failed. Okay, so the short form of the story is we did build a system, and the very, very first prototype, we worked with prototypes in kind of this research mode. The very first prototype, the government said, wow, we could really use this to build a very large system. So they spent $300,000 giving us some resources and data to replicate our research prototype in Washington, D.C. And out of that $300,000 project, they actually wrote a number of specifications and requests for proposal, and ended up releasing them, and we competed, and we actually won. So the first project ended up being a $7.5 million project to do this on a big scale. Okay? And that ran for about 2 or 3 years. I built up the team, did the architecture, did the demos to admirals and generals, and responded to the Joint Chiefs of Staff. You know, it was pretty fun participation. And again, another way to short circuit the story is that, if you remember, there were a couple of skirmishes that the United States was involved in. You know, Desert Storm, you know, under the first Bush, and then subsequent other battles and wars. But both of those utilized this technology. And as I had mentioned to some of you before in dinner conversation, this was capability that had never been built before. So if we had enabled one intelligence analyst to cut down the amount of time he would have to search a big patch of the desert, okay, and using all of these different kinds of information, reduce that search area down to only 2% of where you had to search, that's a 50x speed up in, you know, whether or not they could go verify the location of something. So this program was actually viewed as widely successful. It was so successful in the land-based threats that we then subsequently turned it into a system to process underwater threats. Okay, so you can imagine what those are. And that is now a project that has been installed in about 200 different locations around the world. The key idea is always still intelligence fusion, putting together lots of disparate kinds of information and disparate resolutions, epistemological foundations, currency, and still try to make sense of it all. Out of it, in order to deal with the GIS component of this technology, we found Michael Stonebraker. Michael Stonebraker had founded this company, I think it was called Relational Technology Incorporated, okay? And the product was something called Ingress. Now, it turns out there was another company called Relational Software Incorporated. Anybody know what relational software turned into? No. Oracle Corporation. Okay, so those two were kind of neck and neck in 1982. And when I did the evaluation to say, what do I like, what do I not like, you know, the products were pretty on par. I know I'm on record, but the real difference between the two organizations was the RTI guys would talk to us in a nice technical way. The Oracle guys would say, you just have to buy this. This is the best software. They're much more sales and marketing oriented. So it's kind of indicative, you know, how these companies grew. Okay, now, one of the components that we built was a hypertext system, because we envisioned this analyst workstation as an ability to click from information and go to other information. And keep in mind, this is let's see, what was it? Early 90s. Okay, this project went from 87 to about 92. Okay, so right around 1991, what happened? What was a really important development in 1991?
Yep.
The very first Mozilla browser was released. Okay, and I downloaded one probably a few months after the initial announcement. Jackie probably did the same thing.
That is chicken and egg. How did you download if you didn't have a browser to download? Okay.
FTP.
I know,
You know
of course.
something called FTP?
FTP and BBS and yeah, of course.
That's right. By the way,
We used to live before them also.
Well, there was a browser that didn't do hypertext, but
Yes,
allowed
Gopher and Gopher also. What is that?
Gopher, that's right. Gopher was there, and what was the
And links. Also.
links.
Contextual links.
Yeah,
Links was text-based.
Yeah,
that's
but
the point, but you could still download it from links.
That's right. And what was the hot new protocol that everybody thought was going to take over the web? Take over the internet.
Yeah.
HTTP.
No, it wasn't FTP.
HTTP.
It wasn't HTTP. That's the web.
Peer-to-peer, not peer-to-peer, not.
Here's IRC.
Good guess, but that was a chat protocol, okay? The
Yes.
hot standard that all the standards committees were behind and tried to push was something called Z39.50. WAVE, Wide Area Information System. You never heard of that, right?
I think in the different layer of data, on telecommunication layer of data, or
No, it was designed to do exactly what the web actually did do. It was supposed to be the smart way to extend Gopher. And all the standards bodies went behind Z39.50. In fact, you know, I had our engineers that left the company thinking, wow, this is going to be hot. They wanted to formed the next new hot internet company, or actually the first hot internet company. But it turned out that was so standards-based and, so monolithic and so well-specified that it was too strict, too powerful, and HTTP was, one guy, for sharing physics papers, very simple, and that's what ended up being very simple for everybody to develop. Anyway, that's a little bit of an aside. Okay, so one of the things we had to build was a hypertext system. And so my key guy on the hypertext project was a guy named John Rothermel, R-O-T-H-E-R-M-E-L. Really, really mild-mannered guy, but one of the geekiest guys I've ever met. And I say that in a good sense, okay? He found a seminar that was being given in March of 1992 by this guy named Doug Engelbart. And he said, hey, this guy claims to have invented, linking and claims to have invented all this hypertext technology. Let's go to the seminar. So since we were government funded and I was the principal investigator for this project, I said, okay, fine, we'll do that. We did this, and we invited some of our government, I believe we invited some of our government people to attend this as well with us. Yeah. And so this turned out to be, I believe, one of the two times, I only know of 2 times that Doug gave this multi-day seminar. I think this was one time in 92, and the other time was in 1997. It was actually fairly well attended. It was at Stanford, it was at Skilling Auditorium, went for an entire 3 days. And oh, by the way, every one of those sessions is available on video. So as a historical artifact, if you want to, you can go back to the March 1992 Bootstrap seminar and watch every one of those sessions. Okay? All right. Why is that important? Because we got to know Doug. We thought that Doug was a technologist because he was responsible for hypertext. Turns out he's the very first person to say he's not a technologist. He deals with technology. He's familiar with technology. He has a double D degree, but that's not really why he cares. Okay? And I'll tell you that story a little bit later. Okay? So anyway, just to finish up, actually I'll probably come back to this after I talk about Doug. So let me talk about Doug a bit more. Okay, so Doug, now let's shift gears a little bit, okay? Doug grew up, I think in Oregon. He went to college at Oregon State. Again, I'm doing all this from memory here. And, decided to enter the Navy and became a radar technician. And this, the fact that he was a radar technician, was actually, I think, really, really key to all of this, okay? Number one, he had a lot of spare time. Number two, he was stationed in the South Pacific. And where he was stationed was this little cottage that was called the library. And there was this book in the library by Vannevar Bush that discussed, the seminal ideas, the MEDEX, the information navigation kind of ideas. And so he read all of this, okay? Now, couple that with the fact that, what do radar techs do? Radar techs look at scopes. Scopes are inherently two-dimensional information. All of computation before that was numeric. You ran your algorithms, you ran your, put your data through there, and then you got a bunch of printout. The printout, you had to go and read. If it didn't work, you had to go debug, for printer output. But you weren't necessarily working in real time with the data. As a radar tech, Doug was very familiar with this idea of working with information as it's happening. I think that's a real key notion. Okay, so this 2D representation of information was really, really key. He was the very first, that I know of, to propose managing information, not just numerical data, but actually symbolic information in 2 dimensions. What did that lead to? Led to, let me finish talking about his Navy background. So he got out of the Navy when he was pretty young. He was 25 years old. He got a job pretty readily. He got married. He was out of the Navy, and he thought, I'm pretty happy. I got no problem. Is this going to be the way my life goes the rest of my life? He didn't see a purpose.
Just being happy.
That's right. He didn't see a purpose for himself. He said, every day is kind of good, How am I going to apply myself?
American.
And that, to Doug, was a problem. Okay? Now, what did he do? He started thinking. He started thinking about.
Zoom one.
Okay, all right, let me zoom into this particular area right
You
here.
can also bring like board a bit closer.
Let me zoom into this area right here. Okay? Now, he wasn't the first. He read a number of people. But he was the first to really internalize that the world growth is unchecked. You know, way before, what's the guy at Stanford? Paul Ehrlich. You guys know who Paul Ehrlich is? He's the first guy to write about the population growth problem. He wrote a book, I think, called Zero Population Growth. But in that era, it was a very new idea to say population growth drives all else. It drives food consumption, it drives energy production, it drives pollution, it drives crime, it drives class disparity, it drives all these things, okay? So Paul Ehrlich, I think, wrote his book in the 70s, but Doug had realized this when he was 25 years old. It was about 1950, approximately, sometime in the 50s. I'm not saying he's the first, I'm just saying he decided to take this very personally. So all the problems that we call wicked problems, are going to be worse and are going to be compounded if we don't learn how to stabilize ourselves and learn in a sustainable way. They didn't use the word sustainable in those days, but that's what he was thinking. So he asked himself, what can I do to help humanity prevent this from being our downfall? That's the key question. Okay? So he was thinking, okay, so should I purify water? Should I boil water and give it to people? Should I give food to people? Should I give money to people? Should I do whatever? Okay? And much as we would all realize, if we ask those questions, they're all too big. You know, all of us can try to do in our own way what we can, or you can do things, but it's that proverbial drop in the bucket. He's trying to say, where can he have the most impact? So in his analysis, and keep in mind, he thought about this for quite a while. He finally decided, if we're going to make significant progress, no single individual is going to solve this problem. No single company is going to solve this problem. No single country is going to solve this problem. No single continent is going to solve this problem. Because these are worldwide problems. They know no boundaries. So there's going to be, in particular, no single hierarchical organization that's going to address this problem, get enough resources, and then solve it. Which means that in order to solve these problems, or even make any significant progress on these problems, we have to have continents, companies, countries, individuals coming together and working together, right? There's going to be no boss, no God, no admiral of the United Federation of Countries or whatever, you know, that's going to tell everybody what to do. So that's a very different working model than what had been state-of-the-art. Okay? State-of-the-art is you have a boss, the boss tells people what to do, the boss gets to fire you if you don't do a good job. But in this model, nobody can fire anybody. Right? All you can choose to do is disengage or engage. So, going another step beyond this, he said, in order for people to work together, we have to be able to manage information and communicate. But I'm going to give you copies of all this.
I'll just put you all of it, just
Okay?
use this meeting.
Yeah. So this working together requires sharing of information and being able to mutually develop on this information. All right? So he said that inspired him. That inspired him to go get a PhD. And at that time, again, they didn't have computer science, per se, degree. So he went to go get a degree in double E, electrical engineering. And that was successful. He went to UC Berkeley and got a job at SRI when he came out of there. And found his very first organizational surprise. It's basically the surprise that Dino shared with us, I think it was yesterday morning. Okay? People said, these ideas here, we're going to use computers to do symbolic, stuff. They didn't even use that term, to process words and ideas. That's not good for your career, what he was told. So his bosses said, hey, go work on these other problems, but don't work on these crazy ideas. And in fact, I just indicated here. Resident here. Okay, so that's a brief recap of Doug's personal journey. And I want to just go back here to where Doug and I kind of joined up in 1992-93. By the time 1992 rolled around, he had, no, I'm going to talk about this later. I'm going to talk about what he did in the 60s and 68. Okay, so let me zoom back out. And this is intentionally a little bit busy because I want to get a point across. What is the point? The point is, even if he calls himself a non-technologist, he accomplished a lot, okay? Everybody, I think, this week has heard of this 1968 demo that he did up in San Francisco at Brooks Hall. This demo was actually a remote demo. He was sitting in San Francisco, his team was sitting in Menlo Park. They were connected via a telecom channel, and they were in real time manipulating information. Now, what information were they manipulating? I want you guys to really appreciate this, okay? And let me zoom in first on this left side of things. Okay? He was directly interacting with information, okay? Meaning he had words. And these words were actually being created in real time as he typed at a keyboard, okay? Not one of these key punch machines where he actually had to feed it to a card reader. He was actually feeding letters and words into a system in real time. And seeing it on a two-dimensional screen. That's also a new thing, okay? Bitmap displays. This is new. Manipulation of sentences. We don't even have that today, by the way. We have this thing called word processing. It's a very unfortunate choice of words. Because people think it's words that we're managing, okay? He was managing ideas. Okay, these ideas were first-class objects in his system, and now you guys understand all this, was represented by a real object, a real node. Okay? These are not just words. So you actually take a node that corresponded to a real sentence, and then do something with it. Yeah.
In which way, I understand it from my point of view, from point of view today, but how did he manage, let's say, ideas? In which way did he have some like ontologies there, or maps, or what? In which way it was different?
Okay, so I think the notion of ontology wasn't in his lexicon. Okay?
Yeah.
But what he did have was a way of structuring information. So he had this notion where you had an idea, and then under that idea you could have component ideas. Let me show you. I wasn't planning on doing this, but let me show you. This is not his work, but I'm going to show you what this could look like. Okay, so imagine you have a way of forming an idea, okay? So let's say,
Okay.
can you see this?
Yeah, I understand.
So this, here's an idea, this one right here. This idea right here, right? I just typed it in, okay? So if I want to form a sub-idea, okay? It contains this idea, and this idea, and this third idea. So this notion of structure he introduced in this demo in 1968. This is outline processing. This is structured content. Okay? So he was one that said, it's not just a string of characters. There's got to be a way to, structure it in such a way that you can do something useful with it. So this, by the way, is not his system. This is a program called Echo, ECCO. I use it to take notes. Just as an aside, if I go back and look at September, here are all my notes from September. I can go back to a particular day. Look at all my notes for that day. Oops, there's my password. Never mind. I can go back to another day and look at it. Okay. So the notion is you can look at just enough information and hide the rest. So I can look at one level, I can look at two levels, I can look at arbitrary number of levels. He had this in his system in 1968 called NLS, Online System. Okay? So anyway, this is one instance of an outline processor that was derived from some of his contribution. Let me continue to make these points, okay?
Good.
Sentences are nodes. So you can say, take this sentence and do something with it. Okay? Either move it, copy it, mail it, replace it with something else. A sentence was a first-class object. A paragraph was a first-class object. And then you have this notion of a plex. Anybody know what a plex is in this context?
Plex.
Plex, P-L-E-X.
Okay.
Okay? A plex is, if you take a root node and you have 5 child nodes, all 5 together is the plex. Okay, so that's a set of sibling nodes of a root node. We don't have this notion today in word processing, right? We don't have this in the web, even. But he had this notion of plex. So you could actually take a plex and move it as a first-class object. He had operations on plexes, he had operations on paragraphs, he had operations on sentences, he had operations on words. All of them. Okay? Now, we, meaning the rest of humanity that followed him for the last 60 years, understood some of it. We liked big data displays, we liked word processing, we didn't really understand all this stuff. So all this stuff is still not yet fully leveraged. Outline I just showed you, okay? So now we have an embarrassingly small number of software applications that can do good outline processing. Embarrassingly few. The one that I just showed you, this Echo program, the last update to this program is 1993. It's a 16-bit application that somebody else made into a 32-bit application. It's not even a 64-bit application. Okay? Actually, no, sorry. It's a 32-bit application. It's not a 64-bit application. But it's still the best outliner I've found out there for dealing with ideas, manipulating ideas. So that's why I still use it. It still runs on Windows 7. Unfortunately, it doesn't run on Macintosh, and it doesn't really run well on Linux. As an aside, there was a very good outliner on the Macintosh, something called Think Tank, also around the early 90s. The company was called Living Video Text, and then they created a super version of it called More, M-O-R-E. Great program. I used it to write my proposal to the government, and was very successful writing proposals with that. Okay? But again, died in the mid-90s because stuff like this, regular people don't understand, don't know how to use. There's another lesson learned there we can talk about. Okay, now we get to this thing called, what do you call a pointer that's manipulated by a physical device? Okay, that's the thing he's known for. But look at everything he did. I mean, this is just the stuff I can come up with off the top of my head. Okay, all this stuff. And we'll get through the right-hand side. I'm going through this painstakingly because I want you to understand he was not just the mouse.
He was not just the...
The mouse.
Uh-huh.
It was not just the mouse. Okay, so let me go back and zoom in here again. Remote collaboration. Okay, so what he had was a system where in one room you could have one person working at a terminal or a screen, and in another room you could have another person working at their own screen, and they're connected to the same computer, and they're manipulating the same information. Now, today that doesn't sound so strange. This is 1968. So time sharing was introduced by the guy. Okay? And in fact, after NLS left SRI, that project was picked up by McDonnell Douglas. They created, I think, a subsidiary or anyway, it's called Timeshare, T-Y-M-S-H-A-R-E, in order to try and make NLS available to the general public as a subscription. Just FYI. Okay, let's go and finish the rest of this. Let me show you the right side. By the way, all the red stuff is specific contribution. All the yellow stuff is what we call it today. Okay? So everything was addressable. This is Jack's earlier point. Everything has an address. Everything has a way to manipulate it. You could call it a name. And you could link from idea to idea. This is hypertext. Okay? You can say this word, if I click on it, it will take me to this other part of my repository. We call that hypertext today. Okay? Just as a historical footnote, Ted Nelson also was working on this notion around the same idea. And all this content, Doug did not believe in the notion of delete. No delete everywhere, anywhere. Okay? You cannot delete anything. Okay? His idea was knowledge can be created, it can be changed, it can be aggregated, it can go through evolution, but it is never expunged. Okay? It is an important historical record. So, he created something called version management. So, all of his content, all of his code, it's all in the same system. Okay? He created our first change control system. View specs. This is a very important idea. So, if you have all of your content in this structure, where something has siblings, something has parents, everything in his system looked like that. However, you could present it in multiple different ways.
Yeah.
These are things called view specs. Now, in today's world, you might call it CSS. You might call it, XSL. You might call it XSL. But he had this notion that content was content, and the presentation was separate. So you could have,
It's like XSLT, like XSLT
That's right.
that transforms the data into
right,
the views.
that's right. So that's today. He had this notion way back in 1968.
To simplify the view.
Right?
You don't have the old view.
Exactly. So let's say you had let's say a directory structure, right? So you could have each node could contain different, quote unquote fields of information. The view spec would tell you what you wanted to see in a given presentation format. Or you could actually have a view spec that would go to another part of the document, grab part of the document, and show this with that, and your view spec would control that. Okay? Kind of a beginning, very rudimentary beginning of query language. He had multimedia. He had a screen where you could actually see his image, and you could actually see text at the same time. Okay? So the idea of using different components of a display, different screen areas of a display that contain different information, related information, was introduced by him. And I referred to this before. There's a single, consistent representation for everything in the system. Okay? What does that enable? It enables a lot of different applications to be written on exactly the same representation. Okay? So if you want to sort, you can write a little bit of code because every plex looks the same. If you want to write something that adds a particular kind of, let's say, new information, you can do that to any component in NLS because every part of the system looks exactly the same. So these little bits of code were fairly easy ways to extend the system. Okay? In fact, that's what his team did. Okay? What they were doing was experimenting with a system to run their own research project, and they were writing code in order to provide new capability to enhance the way they were using the tool. I'm going to refer to that later on as well. So this gives you extensibility. Okay? Everything's the same, all this code, very easy. So you have one representation, multiple tools. Now, if you take a look at when the first Macintosh came out, I don't know if you guys remember any of that. Who had the Mac 1? None of you guys, right? Anyway, one of the worst feelings I had in the world was look at this thing called Macintosh Word. Or, no, Macintosh didn't call it Word. Anyway, it was their word processor. The thing that had these fancy fonts. The entire world was fascinated by fonts. But I was thinking, so only this program can deal with this document? No other programs can deal with this document? No other program can do the format of that data. It's completely the reverse of this idea. So now if you take spreadsheets, you take PowerPoint, you take Word documents, only those applications can deal with that content. It's a very upside down world. Okay? Doug's world was you had one representation, therefore tools were easy to add to those, and those tools were universally applicable. Okay, I think I belabored this slide probably long enough, but the point I wanted to get across here is that this thing called the mouse is just one of several ideas that Doug innovated. Oh, by the way, I haven't even mentioned things like the coordinate key set. You guys know what the coordinate key set is? I should have thrown those pictures here. It was a 5 It was basically 5, it looked like a piano keyboard, but only had 5 keys on it, okay? But, just like a piano, you could actually hit more than one key at the same time. So given 5 keys and 5 fingers, okay, and you could actually do multiple keys at the same time, how many different patterns can you create?
Five.
I'm gonna wait. How many patterns can you create? That's right. Which is? Which is?
5 factorial.
No.
5 is power of 5 or power of 5.
No. 2 to the 5th, which is what?
32 or something.
32. Okay, so you can do 32. Why is 32 important? Because it's more than 26. Okay? 32 is important because it's more than 26. Because now you can encode every one of the alphabetic characters, every 26 characters, using this with a few others available. For things like punctuation, like period, comma, those kind of things, space, those kind of things. So the theory was this: you use the chord key set. You were clicking. This is A, this is B, this is C, this is D, this is E, this is F, this is G. Okay, so you just go with this binary order.
Morse.
It's not Morse. It's
Light.
basically just a
Light.
symbol. It's Morse light. Yeah. So you can just type here, and you had a mouse over here. And you never had to remove your right hand or your left hand from the mouse. And you never had to remove your other hand from the keyboard. So you never had to take your eye off the screen to look and see if your hand was in the right position and look up at you. You never had to do that. His idea was you're always looking at the information, always are able to edit here, always able to point to things here. And in fact, when you watch his video in 1968, this is what you see. Now today, I have to take my hands here and go to the computer. I have to see whether my hands are in the right position. I have to find out where the mouse is and I have to go back here.
How fast can you type? How fast can you type?
Can he type? He typed very fast. I never actually measured it.
Compared to typing the keyboard.
I don't think he ever achieved like 70 or 80 words a minute. It was not that fast. Probably he achieved upwards of 50 because I've seen him work. Yeah, sorry, Elizabeth.
No, blind typing, right?
Yeah, what?
Blind typing.
Blind typing. Yeah, he can do blind typing. Because he didn't have to look at this thing. He always knew where the keyboard was. Yeah, you can do blind typing here. Absolutely. And this is why on F and on J you have these little dots there, so you know where your fingers are. But still, you have to look for your mouse.
Totally.
Okay, Lazar, there you go. Anyway, there's a number of things that he experimented with, and I've not itemized here. Among them, notably the chord key set. But I just wanted to if there's nothing else that you get from this, it's that even as a non-technologist, this is pretty remarkable. Because what ideas do we have in computer science today that are not in this set? There are some. I can think of at least one. Okay? But can you think of one? What ideas are in prevalent use today that are not on this page?
Well, some of the AI stuff, right?
True. He did not believe in AI, that's right. But that's not prevalent either. What about, human actual use? What idea was innovated that he didn't come up with? I'm not saying he invented everything. There are things he didn't invent. But name one.
I know. The shooter games.
Okay, I'll give you that one. That's
When
true.
you take a gun and
Right. He didn't have the technology to do animation and rendering and all that. I'm thinking even simpler. Come on, you guys gotta get at least one.
What technology or what?
Yeah, technology. Widely used technology. You use it every day. It's in computer science or computer industry that Doug did not innovate. I just want to know that there have been other contributions.
It's difficult to get out of his domination.
What?
It's difficult to get out of his domination now.
Well, that's precisely the point. Alan Kay has been quoted multiple times. Alan Kay is, one of the guys, one of the very first guys in Mac at Apple, and he's one of the biggest names in computer science. He and Adele Goldberg have created Smalltalk 80, which is a language of Xerox PARC. He is quoted.
What is his idea about remote servers, cloud, computers, peer-to-peer technologies?
Sure. But you could say, he had client server, but he didn't have the three-tier architecture. Right? No, I'm even thinking something much more basic than that. Anyway, I'll let you think about this. We'll come back to it. Okay? All right.
He didn't do that on computer.
All right. So
But
let me get to the next half of the story we're done. Okay? And that is his team built tools, but they explicitly built them in this way. That they had to apply the tools and watch themselves adapt their behavior because of what the tools could enable them to do. And then, because the behavior was adapted, then they knew what next to build into the tool. Very simple concept, right? But most companies still don't do this today. Okay, so he called this the human system, tool system coevolution. Okay? In other words, as I use a tool, here's my human system, here's my beliefs, my rules of engagement, my practices, my procedures, my quality standards. The technology will affect how I do things here. So I better adapt, right? Otherwise I'm not making good use of the technology. But as I adapt, now I identify new things that the technology can help me do. Okay? Maybe it can help me do automatic tests. Okay? Whereas before I couldn't do that. Okay? Maybe it enables me to be able to write down procedures and inform people when these procedures change. Okay? That's a human system change that is clearly enabled by technology. And now if he wants that, what kind of notification does he want? Right? Does he want it after 5 minutes? Does he want it in real time? That affects how the tool can be. So his idea was these cycles, tool development and human system behavior development, have to co-evolve. And they're both cyclical and they both inform each other. Okay, that's the coevolution model. And it's iterative. Now, for those of you in the computer science business that work in teams, this is a word called agile. Okay? Agile. A-G-I-L-E.
Oh, that's fine.
Okay, let me zoom in on that. Click it. Sorry. Click it. And zoom in. Okay. Hopefully that's big enough for you. Okay. Agile was a word coined around the mid-90s, about 95 or 96. But Doug was kind of practicing the key elements of Agile way back as early as the 60s. And today, Agile is widely known to contain very, very simple principles. But among their simple principles are do things in iterations. Okay? And if you do things in iterations, then you have to accept that each iteration is incomplete. And the other notion is, after each iteration, you sit down and you do something called a retrospective. Because the retrospective is where you ask some very important questions. You ask, what should we do more of? What should we stop doing? Because it didn't work. What should we start doing? Because now we think that might help us. Okay? And how does this now set you up for the next iteration? So that you can do things in a way that you think is going to work better than the last iteration. And if you shorten these iterations, then you do these retrospectives more often, which means that you're learning faster. That's the key idea.
Yeah, and you know what was the good, what was bad, what we can learn, what we done bad, and now in next iteration you can change it.
Exactly.
And even more, that you can, let's say, to all your stakeholders, you can see, this is what we have, now give us an idea. If they went in the end, they will just say, oh, we have many ideas, but sorry, but it's too late now.
This is a classic problem, right?
Yeah.
Specify a problem and say, deliver it in 18 months.
Yeah.
Right? Now, what if you just took that 18 months and created these checkpoints called iteration? Either 1 month or 2 weeks or 6 weeks, whatever you choose, okay? But if you're able to ask those questions at the end of each iteration, then you think you'd be much closer to delivering what you really want? Probably. Okay. Now, there's other ideas in Agile too. I mean, one of the ideas that was not in practice, according to some members of the team, is this idea that modern Agile says is very key, which is when you sit down to a retrospective, you take off your title and you put it aside. So everybody is equal in a retrospective. Nobody has a title. Okay, that, by the way, I refer to because there was some team dynamics that evidently, kind of ended up splitting the team. So we have learned
Doug's team.
Doug's team, right? Not just Doug's team, but many other teams as well. So yes, we have learned things. We have learned to evolve more ideas other than just what Doug was practicing. I just always want to refer to that. I mean, there is a lot of progress since Doug. I just want to put him in context. All right. Now, why do I think this is important? If you look at the previous slide, it's mostly technology. Now, name one human system development that we attribute to that.
I don't follow you.
Yeah.
What the, huh?
Can you rephrase the question?
In other words, we know what Doug's contribution is in technology, right? But he believed that technology was half the solution, right? He believed that the human system evolution was also half the solution. He sincerely believed this. But the rest of the world does not know him as an organizational design expert. They don't know him as a systemic innovator, right? They know him as an inventor. He can think systemically, but in actual practice, he needed other components. That's the key. So, I take a look at this. This is the human system side of the picture. The claim that I'll make, okay, and this is not proven, is that the evolution of human systems has not kept pace with the evolution of technology. I'll give you a few data points, okay? People are still generally not happy. We've got gobs and gobs of compute power, but why is it that we haven't figured out how to be happy? People have a limited set of techniques to resolve conflict. One of them is war. We still mostly work on hierarchical organizational structures. Do we think this is going to solve global problems? Probably not. This is one of my favorites. In an organization, in a board meeting, we typically still conduct ourselves according to Robert's Rules of Order. I think the last rev was somewhere around 140 years ago. There may have been some other revs like his son, but mostly it's from 120 years ago. You guys familiar with Robert's Rules of Order?
No, I don't.
That's why I say, we're going to come to a meeting, we're going to have this agenda. For this particular topic, I'm going to give you 5 minutes. After your 5 minutes, you sit down. You only want 3, and you give 2 minutes to somebody else to respond on your behalf or on another topic. And afterwards, we write down what we said. Okay? It's Robert's Rules of Order. This is the way that most companies, most board meetings conduct themselves. Teams don't stay together. This is common. Right? Or they're ineffective. And in particular, if you take a look at Doug's team, his team almost en masse left SRI and went to Xerox PARC. We can ask questions about why. And this is a big, big, big topic. Ego and fear are what you have to design social structures around. People want to achieve. People want to attain. They're ambitious. They are, in some ways, encouraged to be greedy. That's the way society is built. Greed is good. Anybody watch that movie? What movie is that? Wall Street.
With Michael Douglas?
That's right. Greed is good. That was a theme from that movie. Securities and exchange regulations. They're all there to protect society against people who are pathological, who want to steal, who want to go around the system, who want to attain for themselves. Communities are still in conflict. Whether they're geographic communities, principal communities, religious communities, political communities. We even have, whether or not you believe in marriage, less and less of this till death do we part. Anyway, I'm not trying to be too sensational here. I just think that we've had these problems for a long time. We've not made the same kind of progress on these problems as we have on the technology side of things. I want to introduce another model that was another contribution of Doug's, and this is specifically on the human system side. His model was something he called the ABC model of improving improvement. Okay? Now, in his terminology, which I fully admit and I'm very cognizant is not the way we've been using this technology this week. In his model, he had A-level work, which is getting things done. Stuff that actually makes money. Stuff that you actually create organizations to achieve. Okay, like making shoes, like building cars, like providing a service. That's A work. Okay, this is what organizations are created to accomplish. B work is helping A work get done, improving A work, directing A work. Okay? So management is in this category, prioritization is in this category, resourcing is in this category, quality assurance is in this category, providing tools is in that category. Okay? It's how you help A's do better in whatever set of metrics you want to apply. Well, Doug's notion was if B's improved A's, what would happen if we improved the way B's work? Now, if you were able to take A's and make them X% more effective after applying B techniques, and if B got better, wouldn't you be able to expect better, in fact, much better than X? And especially if you did this repeatedly across iterations. Okay? So his idea was, if you improve the way B gets done, then you'll parabolically improve how A gets done. That was his thesis. Okay? This is the notion of compound interest. Okay? If you get 5% every year, okay, then in how many years will it double? Okay? And in how many years after that will it quadruple? Right? So it's not linear. That was his thesis. Okay? Now, here's an interesting observation that I shared with him, and I think he agrees with me. That is that if B's improve A's, B's have to know the domain of A's. If A is building a car, if I'm going to go in and help somebody improve a car, I pretty much have to know how a car is built. Otherwise, they're going to say, you don't know what you're talking about, get out of here. Okay? So if I'm actually in the business of preparing tax returns, I have to know about how to prepare tax returns if I'm going to improve somebody, help somebody make tax returns better. Here's the interesting thing. It turns out it's much, much less important that C's know the A domain. Okay? Because what B's are doing is in the area of information management, resourcing, prioritization, sharing information, communication. Those are very similar across domains. So let's say I'm in a software engineering group, right? And one of my techniques here is at B is, hey, let's use a wiki. Because now we can manage requirements or manage specification patterns, right? Now, if I'm a C, and I'm looking over here at a dentist's office, and say, how do they document their procedures? They're using paper. They're using, maybe charts, on the wall. I can come in and take the solution from software engineering and come over here to the dentist office and say, hey, I think this will also help you here. And even though I don't know the dental domain, it still has huge impact to the way that office is going to run. So the key message here is, you don't have to know all the domains across A's in order to be very effective as a C. Okay. Here's another key point. A's, B's, and C's are not people. A's, B's, and C's are roles. Okay? So, you can have a B-level role and still be doing A work if the team is short on staff. You can be an A person and still see a C-level contribution you can make by saying, hey, I'm going to take this thing from engineering and I'm going to suggest this in finance people. So people can span these roles. They're commonly primarily in this or that, but they're not restricted to being in this or that. Okay, that's the other number. Okay? And almost nobody is in a full-time C role. I'll give you another reason why. If you're doing a job, okay, if you're busy working on, let's say, washing your car, how would you like it if I came and said, you know, you missed that spot, you can do better with this sponge? You know, you can throw it at me, right? I should, if I was really going to help you, wait till, you know, before you get started or after you're done, okay? Before I start picking, hey, you can do this better, you missed that, hey, just go harder, right? This constant improvement has to be done at the right time. Otherwise, if this is just constantly unsolicited, the way I indicate this is B's will piss off A's if it's not done in a positive way. Likewise, C's will piss off B's. You go to your management and say, hey, you can be doing this better, okay? Do that in the right circumstance, okay? All right?
So you don't think the C could be A and then have again B cycles?
Say again?
The C could be A, like
Yeah.
a full-time job and then have all these meta cycles again?
Yes, I do believe that because a lot of these people, a lot of people here know exactly how to do this better.
He
In
does.
fact, I hope I'm understanding you correctly. Okay? Because A's can really see how management can improve. In every company, the people that know what's going on, you know, even before management does, typically are A's. Okay? They're just not empowered. And so, knowing how to do this job better, you can see that as a C-level function as well.
No, but what I'm saying is C could be a full-time job, where then C
Yeah, I mean, C could absolutely, it could be. It's just,
and then it would have also these B and C layers.
yes, it's better. So in other words, if this is your full-time job, then doing this is your A. But you notice that once you get into this model, you're in the improvement model already, okay? So you understand this, you don't really have to go much more meta. Okay, it's
I'll tell you
unnecessary.
how in Toyota they do things. They actually, whenever they're about to make a change, they ask everybody. So the guy who is doing the actual thing on the car, he has a say, and then the engineer has to change the
Right.
design if this guy needs to, you know, kiss his body too much.
And I think that's a great example. They've taken this, which I've indicated as V-level, I think, but they've improved the way they do this. They've installed a set of procedures and practices and values that allow this to be suggested by anyone. It's not just the testing team. Anybody can pull the trigger, right? I'm sorry, stop the assembly line and say, hey, this is not working. So they've created in their organization a way for this to be improved by anyone. Okay, not to belabor that point, but I just wanted to introduce, not this is the best, but this is just the way Doug was thinking about ABC.